Euiwoong Lee from NYU, and they will talk about new algorithms for and external bounds for K.
Should I read this? Oh.
Like you have to turn it. It's on. You can
Okay. Hey, thank you for inviting me. So it's my pleasure to give a talk here. So today I'm going to talk about a problem called the K-cut, and then show you both algorithms and better extremal bounds. Okay. So let me directly get into the problem. It's like one of the very simple problems. Okay. So as an input, you're going to get undirected graph G, and then we're going to get one integer K. The graph can be edge-weighted or not. I think for simplicity, we're going to focus on the case when the graph is unweighted. And then our goal is to delete the minimum number of edges such that G is partitioned into at least K connected components. Okay? So this is a very simple problem, and then you can see that when K is 2, this problem exactly becomes a global min cut that we like. And then just to make sure that we understand the problem, so if K is 3, then currently the input graph is connected, but if we delete these like 4 dotted edges, then we can see that the graph is partitioned into 3 parts. Okay? So we don't have any restriction on the size or like how these pieces must look like, as long as they are non-empty. Okay? So the two singleton vertices and the rest of the part is a one valid 3 cut. So I think my clicker is slow. So yeah, as I said, this generalizes the global min cut when K is 2. And then the one reason I like this problem is that this problem has been studied from many angles. Approximation algorithms, randomized algorithms, or fixed parameter algorithms. And then all these algorithms actually use various techniques that come from various sub-areas of algorithms. Okay? So for example, this problem was featured in approximation algorithm textbook by Vajrani, and then this some randomized algorithms was featured in some randomized algorithm textbooks as well. So what was known about this problem? Okay. So we can think about the 3 regimes. Okay. So the first regime is when we treat K as a just fixed constant, and then we're going to accept n to the any function of K algorithm as a valid polynomial time algorithm. So this is the first regime. And then the second regime is called FPT regime. Okay? So we treat K as a parameter, and then we are OK with any algorithm that runs in time f of K, f can be any function of K, times n to the constant. But in this second case, the constant doesn't depend on K. Okay? So f of K times a purely polynomial factor. So this is a second regime. Okay. And then third regime is the most restrictive regime in a sense that we want our algorithm to run in like purely polynomial time, okay? Polynomial in both n and k. Okay, so this is the third regime. Okay. So there are like 3 regimes of this problem, and then we can ask what the best algorithm can do for this problem. Okay. And then something about the big O policy in this talk, because like, there are 2 parameters, n and k. So we'll try to only hide absolute constant in big O. Except for several cases when we already have n to the k, then I think we are going to assume that k is a somewhat big constant, but it's a still constant, so n is much larger than k. So often I'm going to hide f of k inside a big O. Okay? So that's going to be policy. Okay? So what we knew about this problem. Sorry, I think. So when k is a fixed constant, okay? So what is the most natural way to solve this problem? Okay. So when k is 2, then one natural way to solve this problem is to guess some s and t. Okay, perhaps or just like we can just fix s to be arbitrary vertex and guess t, and then solve the Estica problem. Okay. So then when k is 2, then we can solve the global 2-cut problem in polynomial time. But if you do the same thing when k is 3, which means that we are gonna guess 3 terminals, and then find the minimum cut that separates those 3 terminals, then this problem becomes a multi-way cut with 3 terminals, and then this problem is already NP hard, even in fact hard to approximate. Okay? So even when k is 3, whether we can solve this problem in polynomial time or not, I think it was open for several years, and then Goldschmidt and Hochbaum gave a first exact algorithm that runs in time roughly n to the k square. Okay? So that happened in 88, and then Karger and Stein in 96 gave a more efficient randomized algorithm that runs in time n to the 2k. Okay? So this was a randomized algorithm, and then finally Thorup gave a deterministic algorithm that runs roughly in the same time. Okay? So that was the first regime. And then for exact optimization, it was known that k-cut is as hard as a k-click. Okay? So, and then we believe that k-cut, k-click cannot be solved in FPT time. So when k is a parameter, we only knew that we cannot solve the problem exactly, but nothing more was known. And then in the most restrictive regime, where we want polynomial time algorithms, then there's a paper by Saran and Vajrani, which gave us two approximation algorithm. And then this approximation algorithm is very simple in a sense that, so what you are doing is that in each iteration, we compute the global mean cut of the graph and increase the number of connected components by 1. Okay? So what I mean by that is that we start from the whole graph, and then we compute the global mean cut. We take it. Now we have two connected components. And then in ith iteration, when you have I connected components, we compute the global mean cut in each connected component, and then take the smallest one. Okay? If we do this, then we're going to get one more connected component, and then we iterate this k minus 1 times. Okay? And then it's not hard to show that this achieves a two approximation. Okay? So this is a very simple approximation. And then very recently, Manrangse showed that if we believe a small set expansion hypothesis, then actually this two approximation algorithm is tight. For any constant epsilon greater than 0, there's no 2 minus epsilon approximation. Okay? So, so in this case, it's more or less completely understood if you believe small set expansion. And then it's a slightly different regime. But if we let opt to be the number of edges in the optimal solution, and then if you want to parameterize this by opt instead of k, then it was known that we can do it in every time, in a sense that there is an algorithm that runs in time 2 to the opt square times polynomial factor, and then solve this problem exactly. And then this was first done by Karl and Thorup in 2011. So this is a problem, and then these are previous results.
Generally, when you do the recursive version, so first you get two cut,
yes.
Then you recurse, and you recurse in a smaller one or in both? Or?
Yeah. So yeah, what I said is so when you have an I connected component, and then you compute the minimum cut in each of the connected components, and then you only choose the minimum one, and then break it. Then you get I plus 1, and then you just proceed in that way. So it's more like iterative, yeah. Okay. So yeah, this table summarizes what was known before. Okay. So I explained you algorithms. So yeah, even in FPT regime, so best approximation algorithm was two approximation from more restrictive regime. And then I told you that so in the exact computation, it captures click. So depending on what you believe about k-click, so the running time lower bound is n to the k, or like n to the omega of k. Okay? And then I also told you a hardness approximation. So we thought about this problem for quite a while, and then we gave several results on this problem. So there are like 3 papers from us. So GLL 18A, B, and 19. And then this KL is a different people. Okay. So, if you want to solve the problem exactly, then our result for unweighted graph is the exact algorithm that runs in time n to the 1.58k. Okay? And then I think 1.58 is nothing but 2 times omega divided by 3, where omega is a matrix multiplication constant. So the best one is 2.3 something, so that gives 1.58 here. Okay. And then our new paper, which I will talk about, gives the algorithm for unweighted graph as well, that runs slightly faster than n to the 2k. Okay. And then we also improved something on the FPT approximation. So the first paper gave just a beta 2 approximation and gave like 1.99. Second paper improved it to 1.8. And then finally, the best current approximation algorithm is due to Karl and Lin, which gave us 5/3 approximation. So yeah, these are our algorithmic results. But another like very, very clean like math question we're going to actually focus on is that given a graph with n vertices, how many exact minimum k cuts can a graph have? Okay. So yeah, so if you think about the complete graph, then and then what minimum k-cuts are, then we can easily see that minimum k-cut is just taking k-1 singleton vertices and then just remove them. Every edge is incident on them. Okay? So that there are like n choose a k-1 of them. Okay? Or like better, we can think of a cycle. Because
it's subset of the edges, right?
yes, yeah.
That is a subset of the edges?
Yeah, subset of edges, yeah.
Okay.
Yeah. Yeah, so if you look at the cycle, then like any way to delete k edges will give you like a minimum k-cut. So this is n choose k. So yeah, so we can see that lower bound is like some factor of some function of k times n to the k. Okay? But this like result of Karger-Stein and Thorup actually it's a perhaps I'm gonna explain later, but this is one good example where analysis algorithm proved like something useful in combinatorics. But then actually their proof shows that for any graph with n vertices, the number of exact minimum k-cuts is upper bounded by n to the 2k minus 2. Okay? So if k is 2, then these things match. Like they're both n square, and then we know that it's correct. But if k is like bigger constant, actually there's like an unknown gap of 2 in the exponent of n. Okay? So the coefficient of k can be like 1 or 2, and then that's the question like we want to ask.
So again, so what is known exactly?
So I think
you don't know whether it's, for the complete graph it's n to the k roughly.
Complete graph, and
then for arbitrary graph, it's at most n to the 2k. And, and you don't know what is the.
So we don't know. I mean, we didn't know. What the coefficient of k is closer to 1 or closer to 2.
In the worst case graph.
In the worst case, in any graph, Is there a graph, where minimum k cut is number of minimum k cuts more than n to the k? Is a question we are trying to ask. I think actually, lower bound wise. As far as I know, we don't know any single graph that has a minimum k-cut strictly more than n choose k. Like beating by 1, I mean, perhaps we can do this, but that I don't know. It's strictly bigger than n choose k.
Okay, so
I think cycle may be the worst case. Yeah.
For every, So k is fixed and n goes to infinity, right?
Yes.
The definition, just to go back, so k is exactly the number of what? No, it's the minimum number of edges to remove so that you have at least k?
I think I said at least k, but I think if you think about it, but actually any minimum k cut should have exact k components because if you have like more than k, then you can just like bring one edge back, and then it's gonna decrease the number of connected components by at most 1.
So here you're not counting the set of edges that you remove, you're counting the actual set of components.
I think, but if you assume that every edge has a positive weight, then actually.
But let's say that your graph has no edges. So
what
is the answer? If the graph has no edges.
Subset is counting how many subset of edges are there.
But suppose there's no edges. Suppose the graph has no edges.
I think I'm assuming that the graph is connected.
Maybe thinking in terms of vertices, like vertex partitions.
No. You count edges, right? I mean.
We cut.
You have subset of edges.
We cut edges.
You remove each of them is removed, and you get k connected components, right? And it's minimal. And you assume the graph is connected, and it counts how many sets are in the
So you assume it's connected.
I assume the initial graph is connected.
There are 0 edges. The answer is 0.
Or like can be 1 or like 2 to the n. That's confusion. So I always assume that the initial graph is connected. Yes. Okay. So this is a question we are asking, and then actually so our answer to this question was like improved bound. Which upper bounds the minimum k-cut by n to the 1.98k. Okay? So the improvement is kind of slim, but still we kind of said that 2 is not the right coefficient. And then I think for this result, we are assuming that k is a large enough constant. Okay? So there's like some plus additive term here. So we're going to ignore it by assuming the k is large. So still a fixed constant. Okay?
So this is for every graph, for every nk, for every graph.
For
all these numbers.
Yes. Okay. And then this algorithm for weighted graph easily follows. Again, our bound is proved by enumeration algorithm that runs in time this much, and then it's going to enumerate all the minimum k cuts. Okay.
So this number 1.98, what is that?
I think it's we don't have a good answer, and then we don't. We think that it's not going to be tight.
But it comes from a recurrence. It comes from a
Yeah.
polynomial equation? It comes from
Yeah, I think so. Yeah, it's it comes from our like strange design of other like algorithms. Yeah, I mean I'm going to show you brief ideas, but yeah,
okay,
okay.
great.
Yeah.
Okay, fine.
Do you suspect a difference between weighted and unweighted cases here?
I think so. Yeah, if you talk about the algorithm, yeah. So I think for k-click, so the best the unweighted algorithm is like n to the omega k divided by 3, and then the weighted. Yeah, I think some people conjecture weighted k-click. Actually, you need like n to the k time. I think a similar thing's going on here. So I think so this algorithm doesn't enumerate the every k cut. Okay, so it uses a matrix multiplication as a black box, and then. Okay.
Yeah, sorry, something I missed. You said for that middle box there, k is bigger than some fixed constant, or this is for any nk for n large enough.
So I think I'm always assuming that n is like growing. Yeah.
Yeah.
And then k
So
k to
for
be
any,
fixed
so
constant.
for any, okay.
Yeah, so I think this bound will have like some factor depending on k, some function depending on k, which may be exponential, which I will ignore. Yeah. Okay, so that's the bound, and then let me show you some ideas behind this bound. Okay. So as I said, there are like actually two previous works. They proved this somewhat weaker bound of n to the 2, okay, or like n to the 2k minus 2. I'm going to ignore this additive terms in the exponent. Okay. So as I said, this is tight when k is 2, but it's not going to be tight when k is at least 3. And then actually, as far as I understand, these two proofs are like very different. And then actually our overall approach is to combine both of them. Okay. So in some case we use Karger-Stein. In some case we use a Thorup. Okay. Then actually we are guaranteed that our algorithm runs in time n to the 2k. And then we are going to show that there is some case actually we can beat like both of them. So and then let me briefly remind you what Karger-Stein was. Okay. Okay, so this is a randomized algorithm, and assume that the graph is unweighted. Okay. And then we start from the whole graph. Okay. And then the Karger-Stein algorithm is like very simple algorithm, such that whenever we have more than 2k vertices, then we're going to sample one edge uniformly at random and then contract it. So once we contract it, then we may have a self loops or parallel edges. So we're going to keep parallel edges, and then we're going to delete self loops, and then just we iterate this process until we have 2k vertices. Okay. Okay. Then at the end, we're going to have like 2k vertices in the graph, which means that if you look at the original graph, these like 2k vertices will correspond to like the partition of the entire vertex set into 2k partitions. Okay. And then at the end, so we wanted to find the k cut. Okay. So what we are doing is that, so out of these 2k sets, we're gonna partition a random, we're gonna arbitrarily merge them, okay, to output k partition. Okay. So I'm not gonna show you how exactly we do this, because like the probability here only depends on k. Okay. And then I'm gonna ignore this. Okay. But this is the algorithm. Okay. So to show you an example, so when k is 2, then we sample a random edge, and then contract it, and then sample another random edge and contract it. Okay. So now we have 4 vertices, and then there are like many ways to combine those like 4 parts into 2 parts, and then we randomly choose one of them, and then this is our one attempt for a minimum 2 cut. Okay. So this is an algorithm, and then let's try to analyze it. So let's fix like one fixed optimal k cut, and then we are going to look at the probability that this survives. This is output by this Karger-Stein algorithm, and then so let's call it S star, which is like k parts S1 star through Sk star, and then I'm going to say E over S star to be the set of edges in the optimal solution. Okay. So here the partial sign indicates the boundary. Okay. So partial Si star denotes a set of edges that have exactly one endpoint in Si star. Okay. And then we are interested in the probability that we find S star in this algorithm. Okay. And then if you think about this procedure, then we can see that this procedure fails if we contract the edge UV in the optimal solution. Okay. Okay. So we want to prove the probability that this doesn't happen. Okay. But then one thing we can think about is that, so when the current graph G has a V vertices, and then the algorithm hasn't failed yet, okay, then this k, optimal k-cut S star still survives even in the contracted graph G. Okay? So S star is a still optimal k-cut in G. Okay? And then one very easy claim is that, so in this graph, number of edges in the optimal solution is at most 2k minus 1 divided by number of vertices, fraction of the entire edges. Okay? So this claim is easy to prove because we can consider random k-cut formed by k minus 1 singleton vertices and the rest of the graph. Then we can see that for each edge, the probability that it belongs to this like random k-cut is bounded by 2k minus 2 divided by the number of vertices. Okay, so this bound is this claim is true, and then we can, when k is 2, this is just like easy fact that the size of main cut is at most the average degree of the graph. Okay, so we have this claim, and so once we have this claim, then we can see that in one iteration of this Karger-Stein, okay, so probability of failure is just on the number of edges in the optimal solution divided by the total number of edges, which is this much, 2k minus 2 divided by v. Okay. Then the probability of overall success is at least, so the probability that we don't fail in the first iteration is this, so 2 minus 2k minus 2 divided by n. And then the second iteration is basically the same, but we have one less vertex. And then we can go all the way until we have a 2k plus 1 vertices. And then some factor depending on k, because at the end we arbitrarily combine these 2k parts into k parts. Okay? And then if you simplify terms in each parenthesis, then we get this, and then we can see that both denominators and numerators decrease by 1, and then they always differ by 2k minus 2. So there's a massive cancellation going on. And then so we finally get this. So we can see that this is a sum function depending only on k times n to the minus 2k minus 2. Okay? So this is a probability that the Karger-Stein outputs this fixed minimum optimal k-cut. Okay? So yeah, so this is a probability, and then we know that some of the probabilities at most 1. Okay? So this proof shows that for any graph with n vertices, there are at most some function depending on k times n to the 2k minus 2 minimum k-cuts. Okay. So this is like Karger-Stein that like easily generalizes the mean cut algorithm. Okay. So and then, as I said, there's another approach which is done by Thorup. Okay. So I'm not going to show you the whole proof, but actually the only thing we're going to use from Thorup's result is like a very powerful theorem, which says that in polynomial time, we can compute like n squared spanning trees of the graph, such that for any minimum k-cut S star, there exists a tree T from our collection of n squared trees, such that if you look at how many edges are cut by this one fixed optimal k-cut S star, then for some tree T, actually it is bounded by 2k minus 2. So in this graph, so this black edges represent a tree T, and then this partition represents optimal 3 cut. Okay? So it means that if you look at this optimal 3 cut and then this tree, then tree is cut by optimal 3 cut in 2 edges. Okay? And then the Thorup's theorem always ensures that there is a small list of trees, such that for any optimal k cut, there exists a tree that is cut very small number of times. Okay? So this is kind of surprising, because like any k partition of the vertex set will cut the spanning tree in k minus 1 edges, and then it shows that for any optimal k cut, there exists a tree where this happens only like twice more. Okay? So given this theorem, actually this gives another like bound on the number of minimum k cuts.
This one. So is that decomposition into trees simultaneously true for all k, or is it like you need to know the k and then you do the decomposition for that particular k?
I think in this, perhaps you need to know k first. Yeah. Okay. Yeah. So, but once we are given this theorem, that it also gives some bound on the number of minimum k cuts, because like again, if you want to do it algorithmically, then actually we have a like n to the 2k time algorithm to enumerate all k cuts. Because what we can do is that we can go through each tree, and then once we fix a tree T, then we can consider all the k partitions obtaining by cutting this tree T into K minus 2 edges and reassemble them. Okay? So this is like another very nice proof to bound the number of minimum K cuts. Somehow amazingly actually like these two proofs give the exact same number, n to the 2K, and then we're gonna like try to improve them. Okay? And then in order to do this, let me give you like slightly more complicated looking, but essentially the same algorithm to enumerate all the minimum K cuts based on the Thorup's theorem. Okay? So this procedure is a recursive procedure. So it is parameterized as 4 things. So the original graph G, and then the tree or like forest f, and then K is K as usual, and then L is the number of tree edges cut by the optimal K cut S star. Okay? So again, the goal of this procedure is to find the optimal K cut S star. Okay, let's say the S star is again the fixed K cut of the graph. And then we are given the promise that if you look at this forest, then this number of edges of this forest cut by S star is exactly L, or at most L. Okay? So initially, we're gonna set F to be this tree returned by Thorup's algorithm, and then we're gonna let L to be 2K minus 2. Okay? Okay? But what this procedure is doing is that, instead of like how this procedure differs from the the algorithm I mentioned is that instead of like cutting all the edges at once and then reassemble them, this procedure is trying to guess one optimal component at a time. Okay? So suppose that goal of this procedure at this step is to guess the last component, Sk star, of the optimal solution. Okay? Then how do we do this? Okay? So we can first guess how many forest edges are cut by Sk star. Okay? So we can guess beta here. So in this example, beta is 1 because only one tree edge is cut by S3 star. Okay? Then we can guess Sk star by cutting this tree or forest in beta edges and then reassemble them. Okay? Okay? And then so once we guess Sk star, then we recurse because we find S star, then we remove S star from the both forest and the graph. And then K is decreased by 1. And then crucially, then we know that, so once we remove Sk star and then look at the K minus 1 cut, then we know that number of forest edges cut by the smaller K minus 1 cut is decreased exactly by beta because we removed S star from the graph. Okay? So if you look at this, then actually, suppose that if you guess the correct beta, then the number of choices we need to make at this step is exactly n to the beta because we are guessing like beta 3 edges, which means that if you the total running time of this algorithm is like again like n to the 2k minus 2 because you can think of this L as a potential, and then in order for us to decrease the potential by beta, then we need to make n to the beta choices. Okay? So overall, the running time of this procedure is n to the 2k minus 2. Okay? This is like just like nothing but the Thorup's argument, but I just made it recursive, which is like actually more useful when we talk about our algorithm. Okay, so for example, so here like we wanted to guess what S3 star is. So we first guessed that this S3 star cuts one tree edge, and then we guess this edge, and then we just remove it from the graph. Okay. So and then as I said, our like approach is to combine those two ideas, Karger, Stein, and Thorup, to get like better algorithm. Okay. So let's try to do this, and then let me introduce some notations. Okay. So let me fix optimal k cut S star that has like k parts S1 star through Sk star, and then let's say that this F is a initial tree given by Thorup. Okay. So we know that the S star cuts the forest in at most like 2k minus 2 edges. Okay. And then here I'm gonna do some bizarre things which will be actually very useful. So I'm gonna normalize weights of the original graph G, so that if you look at the total weight of the optimal solution, then it's again like 2k minus 2. Okay? So now like we are in a situation where if we fix S star, which is like the partition of original vertex set to k components, and then we are looking at how many tree edges are cut by S star, and then what's the total number of the graph edges cut by S star. Okay? And then we kind of normalize so that they are like both 2k minus 2. So they are exactly the same. Okay. And then once we do this, then actually for each component Sj star of the optimal solution, I can define two quantities. Okay. So Gj is a total weight of edges cut by one part Sj star, and then Fj is a total number of tree edges cut by Sj star. Okay. And then since like their sum is the same, so their sum is exactly 4k minus 4, because each edge is counted twice. Okay. And yeah. And then like finally for any number alpha greater than 1, so I'm gonna define this C sub alpha to be the set of all, to be the collection of all subsets of vertices whose boundary weight in terms of the original graph G is at most alpha. Okay. So, and then actually by using the same argument as Karger-Stein, we can see that C sub alpha is at most n to the alpha. Okay. So this again looks arbitrary, but you can see that if alpha is a 2k minus 2, then it says that because like we defined the weight of the optimal solution to be 2k minus 2 of k cut. So it says that so number of 2 cuts which are less expensive than optimal k cut is again bounded by n to the 2k minus 2. Okay? So we are in the same ballpark. Okay? So this is like a stronger statement because every k cut is a 2 cut. Okay, but actually we can use the same proof and then like prove this thing. Okay? But then actually, so given this, then we have another way to this like enumerate all the k cut based on Thorup's approach. Okay? So suppose that we are trying to guess one component Sj star, okay? And then we know what Fj is and we know what Gj is. Okay? Okay? So then one way to guess Sj star is just the usual way. Okay? So cut like Fj edges of the first and then like guess what Sj star is. If we do this, then we're gonna cut like Fj edges from the tree. So we're gonna have like n to the Fj choices. Okay? But the second way is to use a Karger-Stein's approach. Okay? And then look at this collection of sets, which is like C sub Gj. Okay? So by the definition, the C sub Gj will surely contain Sj star. Okay? And then we know that by Karger-Stein bound, we know that there are like at most n to the Gj choices. Okay? So if like Gj is less than Fj, then actually doing this way is faster than doing Thorup's way. Okay? Okay, so this is actually our idea. Okay? But then the question is, can we actually get some significant advantage out of doing this? Okay? A priori, it's not very clear. Okay? Okay? Because even in the beginning, we know that sum of f and sum of g is exactly the same. Okay? So if like Gj is equal to Fj for every j, then we know that we are not getting any advantage. Okay? But then we can look into the bad case, and then ask like whether this can be really realized. Okay? So recall that if you do Karger-Stein way, then we are guessing the Sj star from C sub Gj. Okay? And then but anyway, like we're gonna be happy if the size of C sub Gj is much less than n to the Fj for some j. Okay? So in the bad case, it must happen that the size of C sub Gj is roughly equal to n to the Gj for every j. Okay? And then we know that the average value of G is roughly 4. Okay?
So I'm a bit confused. Don't you mean n to the Fj in the second last line?
Yeah, I think but actually their average is like their sum is the same. So I think Okay. I think I'm being kind of vague here. Yeah, because like n to the Gj is like a very like a trivial upper bound. I mean So so in order for the really bad case to happen, this kind of must be true, and then the average value of G is 4. So it kind of means that if we are really stuck, then actually for some alpha less than 4, if you look at the C sub 4, then C sub alpha, then actually the size of this guy is roughly equal to n to the alpha. Okay? Then our question is like, is that really possible? Okay? And then this is like the one technical theorem we proved. Okay? So we proved that when k is large enough constant, then if you look at we give like this like 3 bounds. Okay? So if you look at C3, okay, then Karger-Stein bound will only guarantee you upper bound of n cubed, but we got like this n here. And then same thing for other values, like C sub 4, we bound it by n to the 2.75, and then C sub 4.66, we bound it by n to the 3.75. Okay? So the upshot is that whenever alpha is between 1 and 4.66, so we got the bound, which is much better than Karger-Stein. again, like these numbers actually look arbitrary, and then some of them actually may not be tight.
C sub alpha does not depend on K, and somehow your bound does. I don't understand.
Sorry?
The definition of C sub alpha does not depend on K, right? As far as I can see.
I think, but we could define C sub alpha because we normalize the total graph weight by the,
But is there like there is the definition there of C sub alpha, which is all subsets whose boundary.
Actually, so what happens is this is like alpha times the optimal k cut divided by k. So I think.
But do you get also bounds on these families, on these combinatorial families, all subsets whose boundary is small, as a function of small, or it's only within the context of the argument you told.
I think we only proved in context of the k cut.
So you don't, but okay. And generally for this family of subsets whose boundary is small, do you know how to?
I think it's kind of how you normalize and what you are comparing to. So I think
just look. I give you a graph, and I look at the family of all subsets of vertices whose boundary is small.
Yeah.
And small is at most alpha edges. How many subfamilies do I have? That's a natural question.
Yeah, I think
I was thinking that you were answering this question, but.
Yeah, I think because I think because I kind of at this point I assume that G is a weighted graph.
Sure, that only makes it more general.
Yeah, but then you can just scale the weights, and then here I'm assuming that the optimal k cut has a value exactly 2k minus 2. So I think the value of this statement. So the most general version, without normalization, is so definition of C sub alpha is that the boundary size of S is at most alpha times the value of the optimal k cut divided by 2k minus 2. So if you define C sub alpha in that way, then actually we give a bound.
And then f of k is becoming f of opt, like.
I think f of k stays the same because anyway we are comparing ourselves to the optimal k cut. I mean I think it's gonna be like actually it's gonna be evident in the proof, and then let me show you how you prove at least the first item. Okay. So actually this is like very simple. So this is again the definition of C sub alpha. And then this is what we want to prove. So the proof, at least in this case, is very simple. Okay. So first, notice that when our set system has strictly more than 2n sets, then there must exist like two sets S and T, such that they cross. Okay. Meaning that if you draw the Venn diagram with these two sets S and T, then all four possible cells are non-empty. Okay. So S intersection T, S minus T, T minus S, and then S union T complement. Okay? So when this happens, then what we can do is that we can delete the boundary of those two sets. Okay? So if we do this, since both S and T belong to C3, okay, so their boundary weight is 3 each. Okay? So we delete at most 6 weight. And then since we know that each of these parts is non-empty, so we know that if we cut these two things, actually then we're going to get 3 new connected components, which is like 4 minus 1. Okay. So this only happens once when C3 is greater than 2n. But I'm not going to show you, but actually we can somehow easily see that if C3 has f of k times n, I think in this case like f of k must be like 2 to the k or something. If C is greater than this, then actually we can do this not only one time, but actually can do like k over 3 times. So and then once we do k over 3 times, then we are going to get k new connected components. So we get like k cut. Okay? And then the total weight we delete is basically we delete 6 in each iteration, and then we're going to do like k over 3 times. So this is like false, but with some juggling actually we can make sure that we reach the contradiction that the optimal k cut was 2k minus 2. Okay? So this bound actually crucially assumes that the optimal k cut has a value 2k minus 2.
2k minus 2.
Yeah.
And the alpha and the, okay. So you're given a graph, you know that the optimal
k cut
is 2k minus 1 edges.
Yeah.
And you ask how many subsets of vertices are there, such that their boundary contains 3k edges.
Yeah. I mean, I think
most 3k edges.
Yeah.
Okay. And you get that this thing is at most f of k.
So and then yeah, if you look at this lemma, then it's like just like easy fact. Like one but fancier way to say is that for any set system with like strictly more than 2n sets, it's a dual VC dimension. Okay, is at least 2. Okay, so you can see that this is exactly the VC dimension of the dual set system. Okay, so in the usual VC dimension, we want points to be shared. Okay, in this actually these two sets, these two sets are shared. Okay, in the dual way. Okay, and then let me, so the same argument, but let me show you how we prove the last item. Again, yeah, this is a C alpha, and then this is a thing we want to prove. We want to prove that C sub 4.66 is at most n to the 3.75. Okay. And then actually, so this only this part change. Okay. So what we proved is that if you have a set system, and then if you have more than like n to the 3.75 sets, then there must exist like 3 sets that cross. Which means that if you look at the Venn diagram, sorry, then actually this 8 cells must be non-empty. Okay. So and then yeah, so and then if we do this, then actually we can do the same thing. We delete on the boundary of all these 3 sets. Okay. Then we pay slightly less than 14, and then you get 7 new connected components. So yeah, so again, yeah, you can do this like many times and then reach the contradiction. That opt is strictly, yeah, so we get a k-cut strictly cheaper than opt. Okay. Again, so like another, like a fancier way to say the same thing is that for any set system with this much sets, it's a dual VC dimension is at least 3. Okay. And then I think actually this 3.75 is totally arbitrary, and then I think it must be 3. Okay. So lower bound comes from like considering all triples. Okay. So if your set system has all the triples, then actually we can see that there should not exist 3 sets that cross. But I think actually I think that should be the example, but we don't know how to prove it. So but actually we can finish the argument for k-cut. Okay. Okay. So this is what we proved. We proved that C3 and C4 are like very small. Okay, compared to the Karger-Stein bound. Okay. And then I think so we can look at the k components in the optimal solution, and then look at what their values, like what Gj and Fj are. Okay, and then for simplicity, we can let's assume that Fj is at least 2 for every j. It's going to be even easier when Fj is 1. And then so we're going to plot Gj and Fj for every j. Okay, so these like red dots represent the each part in the optimal solution. Okay. And then since I already showed that the average value of G and average value of F are like 4. Okay, so the average point is just this green point, which is like roughly 4, 4. Okay. And then if you look at this line containing this green point, then we can see that because like this blue line contains a green point, and then the average of this red point is a green point. We know that there must be a red point above the line. Okay. And then I'm claiming that actually then actually we can guess that point, and then take some advantage. Okay. So because it's true, because like if so there must be a point Gj Fj above the line, and then if Fj is greater than 5, then actually the slope of this line is very steep. Okay, so we know that then actually Fj is already much bigger than Gj, so the Karger-Stein bound will allow us to beat the trivial algorithm. And then when Fj is like 3 or 4, okay, then it means that so Fj is like here or here, which means that Gj is at most 4. Okay? And then, so in that case, just like usual Karger-Stein bound will not give us anything. But since we proved this improved bound, which is like 2.75, okay? So what we can, yeah, so then we know that we can guess only n to the 2.75 sets. And then we're going to decrease our potential by 3 or 4. Okay, so we are winning something. And then the same thing happens here. Okay, so if Fj is 2, then we know for sure that Gj is at most 3. And then we prove this special bound that C3 is bounded by n. Okay? So in every case, actually, we can save n to the epsilon. Okay? In each iteration. So that's only the initial call to the this recursive algorithm. But then question is how do we win like omega k times in order to have a epsilon multiplicative advantage? I think, but yeah, like actually I showed you the whole idea. Just to the remaining work is to calculate every like parameter and then make sure that we this argument is kind of robust. Okay? And then at the end, the algorithm is that initially L is a 2k minus 2, and then we can see that if L is greater than 1.75k, then actually these arguments can be made robust, and then we can always win as above. We can save n to the epsilon every time. And so at this point, yeah, we can guess our optimal component, one optimal component, by Karger and Stein way, and then recurse to smaller k. And then if L is already less than this much, then actually we can just do naive Thorup's argument. Okay. So this was for k-cut. Okay. And then for the remaining time, let me say some more about this dual visit dimension, which is a clean question by itself. Okay. Okay. So recall that the dual visit dimension of the set system C is the largest L, such that there exist L sets, S1 through SL, such that they cross or shattered, which just means that 2 to the L cells are non-empty. Okay. Then as usual, like for the visit dimension, then we can ask how large the set system must be to ensure that the dual visit dimension is at least L. Okay. So I'm going to define this M of L to be the maximum size of a set system that has a strictly that has a dual visit dimension strictly less than L, which means that if your set system is strictly larger than this, then your visit dimension must be at least L. Okay? Okay, so this is the usual definition. Okay? And then I think in this definition, I actually I'm always assuming that C is on n elements. So like one trivial like upper bound is that M is at most n to the 2 to the L. Okay? Okay. Because if C is larger than n to the 2 to the L, but then you can use usual Sauer's lemma for like usual visit dimension. Then we know that 2 to the L, there are like 2 to the L shattered elements. Then actually, then we are done in a sense that, so if in this case, 2 to the L is 8, and then so if C has a more than 2 to n to the 8 sets, then we know that these 8 elements are shattered, okay? Which means that yeah, for these 4 elements, there is a set in C that contains exactly these 4 elements out of these 8, and then this, and then this. Okay. Then we know that we can take these 3 sets. Then actually, these 3 sets are shattered as sets. Okay. So this is like one trivial upper bound, and then for lower bound, we can see that the lower bound is this thing, like n to the 2 to the L minus 1 minus 1. Okay. And then the construction is like just like all sets of size 2 to the L minus 1 minus 1. Okay? And then we can see that this it has a dual visit dimension strictly less than L, because like to be shattered, for like L sets to be shattered, each set has to have like 2 to the L minus 1 different cells. Okay? So this can't happen. Okay? So this is like easy lower bound. Okay? So for general L, so we are like stuck with between this 2 to the L minus 1 minus 1 versus 2 to the L. Okay? So which only differs by a factor of 2, so it may not be like too interesting, but it's going to be interesting to nail it down. And then especially when L is 3. Okay? So it was like just like trivial bound gives like 3 versus 8, but somehow we proved the better upper bound is like 3.75, and then even there like we believe that 3 must be the right answer. There, yeah, I don't have a good idea, but hopefully like yeah, better bound is maybe the right answer. Okay. So and then let me further tell you something about what we did. Okay? So in order to prove the dual visit dimension bound, actually we use like more refined notion called the partial visit dimension. Okay? Actually, which was actually directly useful for our k-cut as well. Okay? So so if like C is a set system, then we're going to say that C is a L comma A shattered. If like there are L sets. Where like if you draw this Venn diagram, then at least A cells are non-empty. Okay? So yeah, so like C has a dual visit dimension L means that C is a L 2 to the L shattered. Okay? And then yeah, we can again define this quantity M sub L of A, which is the maximum size of C, which is not LA shattered. Okay? Then M of L becomes M over L and 2 to the L. And then I think, so yeah, how do we argue about this thing? Okay? So if you look at just like Sauer's lemma's proof, and then think about how we adapt it, I think then one easy lemma we can prove is that, so if you pay a factor n more, then you can increase A by 1. Okay? So yeah, M sub L over A plus 1 is at most MLA times order of n. So the proof is similar to Sauer's lemma. Okay? And then, so actually the main technical theorem we proved is this guy, which says M37 is at most n to the 2.75. Okay? So once you prove this, then combined with the previous lemma, it says that M3 is at most n to the 3.75, as I claimed. And then I think this actually must be n square instead of like n to the 2.75. But then, yeah, we don't know how to prove it. But one thing we know is that, so if every set has a constant size, then actually we know how to do it n square. Okay? But somehow we had a problem with dealing with larger sets. Okay? So finally, let me show you. Yeah, so yeah, this is open question. What is the MLA? So yeah, let me give you like some brief idea about how we handle this. Okay? So I'm gonna show you this like toy lemma, saying that now if every set is a triple, okay, and then if we have like n more than n square sets, then there exists like STU that have like 7 non-empty cells. Okay? So the proof is very simple. Okay? So yeah, so we have like bunch of triples as sets, and then for each pair of elements, okay, so we're gonna call them light if at most 5 sets contain it, or otherwise we're gonna call them heavy. Okay? Then the first operation we can do is to delete all the triples with a light edge. Okay? So perhaps we can do it iteratively. Okay? So we can go each pair one by one, and then ask whether this is light or heavy. And then if it is light, then we can delete all the triples containing this pair. Okay? So we're going to delete a lot of triples. But one thing is that, so each time we're going to delete at most like 5 triples. Okay? So we delete at most this many triples. So if you assume that C is larger than this, then there must be like some triples left. Okay? Where like each edge is a heavy. Okay? And then I'm going to show by picture why we are done. Okay? So suppose that, yeah, this triple is heavy. Then means that, yeah, this pair is heavy. Okay? So which means that there are like many other triples containing this pair. So we fix one. Okay? And then if you look at and then we can look at the other pair. Okay? Again, it will be contained by many triples. Okay? And then one crucial factor we are using is that, so some of the triples may contain the element which already appeared in our construction, but since now like at least like there are like at least like 5 triples, there is always a triple that involves a new element. Okay? So we can do this, and then in the final pair that we can do this as well. Okay? So if you delete the original set, then we know that, yeah, so there are like 7 elements which certifies there are like 7 non-empty cells. So this is like very cute argument, and then you can easily see that this argument generalizes when each set has a size constant, which gives like n square bound. But generally, so somehow we didn't beautifully generalize to larger sets, so we got a worse bound here. But I don't think actually there's a reason that we lose something here. And then again, yeah, this n to the 3.75 is a dual VC dimension bound. Okay, so again, yeah, so this is an open problem for like dual VC dimension. And then if you finally go back to the K-cut, okay? So one thing, I mean, I told you our result, but one thing I want to highlight is somehow analogy between K-cut and K-click. Okay? So I already told you that in terms of exact computation, so K-cut is as hard as K-click. Okay? And then if you look at the best algorithms for K-cut and K-click, okay? At least before like our recent work, then there's like this like a weird analogy. Okay? So the best running time of K-cut is similar to the best algorithm K-click, except it's like weird factor 2 in the exponent. Okay? And then we can ask, okay, like is like 2 really like scientific, or like should it be there? Okay? And then one thing I'm really excited about our work is that at least like in these 2 rows, okay, we proved that like 2 is not the right answer. So it's like 1.98. Okay, actually we should be like much better. And then I think generally there's like no lower bound of a K-cut, no evidence of hardness of a K-cut other than K-click. So right now it's like still consistent with our knowledge that actually complexity of a K-cut should be exactly equal to the complexity of K-click. Okay? So it's going to be awesome if it happens. We don't know any advance from the lower bound side. So it's going to be very interesting whether this to see whether this question is true or not. Okay? Thanks.
Question?
So can you say anything about the proof for n to the 2.75 in the case where the sets are non-ifies?
Yeah, I think, yeah, it's,